profile. Now, based on refractive index profile, also we can classify the fibers into two groups. That is step index fiber. If you see these fiber types based on refractive index profile, based on refractive index profiles, refractive index based on refractive index profiles, it can be step index fiber, step index fiber, step index fiber, and also it can be GI fiber, graded index fiber, graded index fiber. Right. If I'll show you the diagram, actual, it will be more clear. Next figure, I'll different colors. I mean, here actually, step index fiber, the refractive index, you have seen this core clad jacket is here, 3 layers are there for any fiber. So in this, if it is step index fiber, then refractive index is constant in the core. You have seen this core, core cladding. We have seen it last time. I have shown it. These ones, core cladding, and next jacket was there. Right. We have seen these things. So you see, if the refractive index of this core, this is a core, this is a clad, and this is a jacket. So if the refractive index of the core is constant, then it is called step index fiber. But if the refractive index of this core, it is, we generally have to consider this is N1, this is N2, right? If N1 is constant, then it is called step index fiber. But generally, in most of the cases, this N2 remains constant, cladding remains constant. But of course, cladding can also vary. We'll see it. There are different single mode fibers are there. There can be more than one cladding also there. Can be triangular profile also there, etc. Many things are there. Advanced type of fibers are there. But in generally cladding refractive is constant. Only core refractive index can vary. If core refractive index is constant, then it is called step index fiber. But if step index, if the core refractive index is varying, if instead of this the constant refractive index, if it is a function of R, then it is called GI fiber. In this case, the core refractive index will be a function. That means here it will be maximum at the center and gradually decreases on the both side. But cladding refractive index is constant, right? So this is the classification of the fibers based on refractive index, SI fibers and GI fibers. Also their constructions, their geometry. And again, each type of fibers, they can be classified according to the number of modes propagating. It can be single mode fibers, it can be fibers, multi-mode fibers. This is single mode, and this is multi-mode. This is also, it can be single mode fiber, it can be multi-mode fiber, fibers. Just a minute, let me check. Okay, total now 23 candidates, 23 have joined so far. Okay. After these times, I noted the time, how many of you are joined, how many are leaving. Okay. Of course, it is already recorded, but still I am also checking these ones. 24. Okay. It is there, net is there, Harshavardhan? I mean, I'm audible now? Harshavardhan?
Yes, sir, you're audible, sir.
And slide is also visible, na?
Yes, sir, yes,
it is
sir.
fine. Okay. It is showing. Okay. So again, according to the number of modes, they can be single mode fiber, it can be multi-mode fiber, right? But generally, this GI-SM fibers, it is not in practice. It is not in practice, GI-SM fibers, because GI fiber is really difficult to fabricate because within a very small dimension, you have to vary the refractive index, and that is available in the market GI fibers, GI fibers, but GI-SM fibers is not in practice. That is because of the fabrication cost, right? So generally 3 types of fibers are available in the market: SI, SM, SI, and GI fibers. Right? We'll see their applications and their advantages. Before that, you see their geometry and the dimensions. But earlier we have seen it in data communication, but now we have to see in details, because based on these things you can implement the battery system. So for low bitrate systems, high bitrate systems, and depending on the availability of the sources, and if suppose you are having LED sources, then all the type of fibers cannot be used, right? A specific if laser sources are there, then what type of fiber can be used? So you have to know the detailed dimensions of those fibers, then only you can choose the sources, or you in other way, if you have a source, you can choose the typical type of fibers. So see their dimensions, then it will be more clear, and also their geometry, structural geometry, core and cladding. So I think if you see this figure, then it will be clear what it is called step index, it is Gallard index. So this is diffractive index, x-axis, and this is the distance from the axis, fiber axis, that is R, right? And if it is step index, and then it will be something like this. These ones. So this is actually, you see, a sudden change of refractive index from core into the clad. And you see, this is actually the core. This is the core. And this is the cladding. Right. So this is the fiber actually here. And this is this one, right? And this is the fiber axis. Fiber axis. So you see, this is a step index fiber. So there is a sudden change of refractive index from N1 to N2 or N2 to N1. This is maximum refractive index, it is N1. You see here, and it is constant throughout the core. You see, throughout the core, it is constant. Within the core, this is N1. This is N1 is constant. And next, there is a step change or sudden change of refractive index from core into the clad. As soon as you go from core into the clad, there is a sudden change of refractive index, that is N2. And this N2 right? Actually, it is equal to n1 into 1 minus delta. This delta is a fractional index difference. The delta actually it is n1 minus n2 upon n1. This term is used for fiber design. We'll see in the design aspect that times also if it is not mentioned, you have to assume this value depending on the type of fibers. But you keep in mind this is the fractional index difference, this delta, right? So that is actually n1 minus n2 upon n1. And next you see the GI fibers. In case of GI fiber, it is not constant as I mentioned. So in this case, you see it here. You see. So in this case, this is your core and this is your clad. This is repetitive index and this is R. So you see it here. Here repetitive index, it is not constant. You see it is varying. Some profile is there, right? So in this case, here it is of course N1. At the center of the fiber axis, it is N1. But in both sides of this fiber axis, it is a function of R, NR. It's varying, right? And but at the cladding, it is constant. You see, it is constant N2, right? That is here into and also it is into 1 minus delta. Of course, delta it is something different that will see it. But, of course, if this repetitive difference is small, then of course it will be similar to this value n1 minus into n1, right? When we discuss the GI fiber, at that times we'll see more details about this repetitive index profile. But in general, this repetitive index profile, it can be either parabolic profile, it can be linear profiles, or it can be parabolic profiles, etc., etc. Other complicated profiles can be there, but mostly it is parabolic profiles. In that times, one factor is used, alpha. If alpha equal to 2, that means it is a parabolic profile, repetitiveness profile parabolic. So these things are there in GI fibers. So GI fiber repetitiveness is not constant in the core; it is varying, right? Now, if you see the dimensions of SI fibers, GI fibers, quite clear now. Now, in case of now, if you consider the SI-SN fiber, SI-SN, the dimension this is actually twice A. This is twice A core diameter, and this is the 2B cladding diameter. So SI-SN generally twice A, it is 2 to 10 microns. It's very, very thin, twice A, cladding core diameters. And 2B, it is 125 microns. Minimum, it should be, I mean, it's not be not less than 120 microns. 120, we'll see it, why it is like these things. Yeah. I mean, not less than 60 micron radius. This radius should not be less than 60 microns. If it is less than 60 microns, then it will not be optical. I mean, it will not it will not trap the optical energy. Rather, it will be leaking. Optical fiber means their energy, if supply energy is launched, that will be well trapped within the fibers. So that is possible if it is the core radius, it is of 60 microns, or the diameter should be minimum 120 microns. Beyond that, it can be more, but if more means more material will involved, then also it will not be optical fiber. The heavy cables will be there. Optical fiber should be very thin, right? So in case of SI-SN fibers, this is the dimensions, and in case of SI-MM fibers, is quite large, twice A. It is generally 50 to, it may be quite large, 50 to 200 microns. 200 microns, it can vary, and 2B cladding diameters can be 125 to 125 to 400 microns. That is SIMM, right? And in case of GI GISM is not in practice, so GIMM fibers, it is very similar to the SIMM. Here twice A, it is 52 generally 100 microns, 50 to 100 microns. Core diameters, and cladding can be, it is around 125 to 150 microns. 125 to 150 to 200 microns. 150 micron, like these things. Right. In this range. So that is GI fibers. Right. Now, it is quite clear now, based on the dimensions, you can have their advantages, disadvantages. So if you consider this SI-SN fiber, that is very, very useful for very, very long distance systems. For very long distance, it is useful. Long distance. Why it is so? Very thin, less power will be propagations in this case, but whatever the power is launched, that will be that will propagate without any distortions, or without any attenuations, right? So very long distance undersea cable systems, I told you, so one continent to another continent, even the longer distance as well as undersea cable systems, that is the SI-SN fibers. And that is because of their very high bandwidth. Very high bandwidth is here in case of SI-SN fibers, right? Because here dispersion effect is less. So that's why it is very, very useful for high bitrate systems, means high bandwidth fiber. Right. Whenever you need high bandwidth fiber, high bit rate system, that time you have to consider SI-SN fibers. But their fabrication is little bit difficult compared to the MM fibers. And also here, of course, one drawback is SI-SN fibers. Only source that can be used is laser source. Laser source can be used here on SI-SN fibers, because if you use the LED sources, I mean, I told you incoherent sources, then this fiber there'll be no light. Their dimension is very, very thin. So if you use the conventional sources, then very, very less light will be coupled, right? So to couple light efficiently, you have to consider the laser sources, which is more directionals. So the restriction here is here only laser sources can be used. But once you use the laser sources, some other problems will be there. That we'll see it when we discuss the laser sources. That we'll see it. Right. You can have several advantages, but you can also simultaneously there will be some limitations are also there, right? In case, because some noises will be there. Say coherent noises will be the speckle noise, coherent noise. Those also will be come into the picture. There are some methods that to overcome all those things. That is the SI-SN fibers. Now another class is here, that is SI-MM fibers. Here you see here it is fabrication is very easy. SI-MM fibers, the dimension is large, but it is not useful for long distance systems communications. For short distance, it is okay. This one, and the bandwidth is also not so high. because of multi-mode propagations. Multi-mode, many modes will be there. You see here data rate, it is not so high. So for example, in a field, if say 10 persons are running, and if the 10 persons they're reaching the destinations at different instants of time, then you see if you plot a pulse, that will be broadened, right? So time difference will be quite large, right? So, but if you that is the case of multimode fibers, right? That means if you launch a pulse, then after that pulse will be distributed among different modes and energy. And if these modes, if those modes are they arrive at different instant of times, then this pulse shape will not be same as the launching pulse. Rather, it will be after certain distance, it will be broadened, right? So if you launch very short pulses very close together, say for high bit resistance, then there'll be a lot more pulse will be there. So ultimately, it will be like these things. You'll not be able to recognize the original pulse. So that distortion will be there. That is a dispersion effect, one intermodal dispersion effect. So that will actually limit the bandwidth or the data rate in case of SIMM fibers. But for short distance, it is easy for laboratory purposes or short distance communications. SIMM fibers are widely used. Right. In this case, another advantage is here, apart from the fabrication process, advantage is that you can use any type of sources. If you have MM fibers, you can use both type of sources, LED or laser diode, laser sources. Both the sources can be used here. Because dimension is quite large, so you can use LED sources as well as laser diode sources. But they're having problems of the dispersion limitations, right? So that is the SIMM fibers. And if you consider these GIMM fibers, here actually bandwidth will be quite large in GIMM fiber compared to the SIMM fibers. And in fact, this is varying. That is to increase the bandwidth, right? And the profile, certain profile is maintained. If you see there how the rays are propagating, you can see it here. This is the single mode. In single mode, only axial ray will be there. You see it here. Dimension very thin, so that is the single mode fibers, right? Core dimension is very thin, and if it is multi-mode fibers, then it is like these things. In this case, you see many rays will be propagating here, right? Different angles, like these things. The many rays will be there. That is the SM fibers, SISM fibers, SISM fibers. This is SIMM fibers. And for GI fibers, for GIMM fibers, the rays will not be straight line because refractivity variation is there. So in this case, you see if this is the axis, then their propagation is like these things. It is not the straight line, it's like these things, right? Like these things in GI fibers. Right. So they're the different, this is GI fibers, right? So there are different propagation types of propagations in different types of fibers. Here only axial rays are there. Actually, we'll see it. The SI fibers, this ray optics is not be useful. Here the wave optics is here, and in fact, single mode is propagating. SM is single mode. That mode is a particular mode is here, which is called AG hybrid mode, AG11 mode. We'll see it. We'll see the mode theory. That time it will be more clear. Anyway, so this is there are the different types of fibers, and there are different advantages and disadvantages of GI fibers is very difficult to fabricate, right? I mean, costly. because you have to maintain particular profiles within the core of the fiber. And as you have in the core, either it could be parabolic profiles or in some linear profile or some other profiles would be there. So you can see it here. The bandwidth is moderate in this case. Maximum bandwidth you can have it in SI-SM fibers, and MM fibers you can have moderate bandwidth, but it is greater than GIMM fiber bandwidth is more than this SIMM. That's why in metropolitan cities GIMM fibers are used, where bandwidth is large, as well as you can use any type of sources because this because of these multimode natures, right? But here these splicing fabrications, these processes are difficult in case of GI MM fibers, right? So metro city generally these are used for undersea cable systems or very long distance systems. These SI-SM fiber is used, and for short distances within buildings, central offices, right, among central offices. So these MM fibers are used, short distance systems. Well, the different types of fibers, we have seen it. Now let us focus before going to the little bit about why I'm saying that sometimes you can use the rays and sometimes you can use the waves. So where you can use the rays to explain the propagation of energy, or where you can use the modes or waves. Mode means mode. What is the meaning of mode? Means a particular field distributions, right? So let us see, let us clear the concept of these things, then it will be clear when you use the ray optics, when you consider the wave optics. So consider the basic, I mean, methods, the methods that can be used for propagation of energy, methods for propagation of energy, light energy, obviously light energy in optical fibers. The two methods are there generally. One is ray optics method, other is wave optics method. Ray optics method, other is wave optics method. But when you consider the ray optics, when you consider the ray optics, that is some tricky easier. If you see it, that means you have to know the limitation of the ray optics, and also you have to know the condition for the wave optics, right? So for this, let us consider a point source. It will be clear if you just in this context you must be knowing that ray optics is very simple to implement, but wave optics a lot of mathematics will be involved, because you have to consider the Maxwell's equations, you have to take wave equations, you have to solve the wave equations, the boundary conditions. So those things will be there in wave optics or mode optics. But ray optics is simply use the geometrical optics, rays of I mean reflections, refraction, those things are being considered in this case. So to know exactly what is this ray, you consider a point source and a aperture, and consider a screen. This is a screen, not the reflecting surface, is a screen. Dash. This is AB, the aperture. And this is the point source P. Now, if this aperture is large, means few centimeters, few inch to few centimeters, then you see what will get it in the screen. A circular patch of light, isn't it? A circular patch of light, you'll get it here. And outside there is a shadow, right? Shadow is here, dark is here, and this is the bright. This is bright. You'll see the bright patch, right? This is the case, you'll get it. Now, if you start decreasing this aperture, this A, and it's very, very small, of say millimeter, the same, then you see, can we say anybody what you get it in this case in the screen? Same thing you'll get it, or some other things you'll get it. Anybody can suggest? Any one of you? What I can see in the
Interferences.
interference?
Multiple sources
Actually,
will have. Dark regions in between them.
That means actually you'll get not circular patch of, you'll get some patch, but at the same times you'll get like these things, some pattern also you'll see it exactly. You'll get some pattern, isn't it? That means here you'll see it a circular patch of light with well-defined boundary, shadow and dark and bright, isn't it? Light and dark, you will get a sharp boundary. But in this case, if this aperture is very, very small, order of millimeters, then you see you will not get the sharp boundary as this. That means in the shadow portion also will get some light, because you see if they consider the ray, it will up to this ones. But after this ray, here see there is no light, though there is no light in here, dimension is large. But in this case, you see beyond this ray, you will get some light, right? That is actually because of interference that we have mentioned. That is because of secondary wavelets, interference of secondary wavelets. So that this phenomenon is called diffractions, in fact, isn't it? You'll get the diffraction effect, right? Now, this diffraction effect can also be minimum if this dimension is very, very thin, as well as if you consider this lambda, you are using some light, you are using light. If the lambda tends to 0, then you see this diffraction effect will not be 0, but it will be minimized. Right? Exact diffraction always would be there to some extent. But if you can neglect this, this diffraction effect can be minimum if you consider this lambda tends to 0. That means in that case, what will get it? Will get a thin pencil of light, see it, right? And that is called the ray. That is called ray. In the limit, lambda tends to 0, right? And that is actually basis of this, the ray optics or geometrical optics, right? In the limit is a path of propagation of energy is a thin pencil of light, where we consider the lambda tends to 0. I mean, it neglects the finiteness of the wavelength of light. Then only you can have the ray. Now, what is this? Why you are considering this? This one? How you are considering lambda tends to 0? Say in a camera. In a camera, you have seen this camera lens. It is generally 1 inch in diameter, isn't it? 1 inch diameter. And in the you see in this earlier camera that you have seen in the back side of this lens, the film was placed. But nowadays also, of course, it is digital camera is here. But anyway, but some lens is here, and image is formed at the back focal, the back side of the lens. Right. If some object is here, the image is formed at the back side of the lens. And this lens is of say few centimeters. And in that case, generally what you are doing it, you are constructing that to get the image, you are actually constructing the ray. Some object is here, then you're considering this parallel ray, isn't it? Like these ones. Next you are considering this some other ray like this. In this way, you are some of PhD, etc. You are considering the you are constructing the rays, and you are getting the image at the rear side of this lens, right? Not all the times you can have the image in this side also, right? Whatever the case, you are considering the rays. Why this ray? That is because this dimension of the lens, it is of the order of centimeter, whereas the lambda, it is of the order of 10 to the power minus, say if it is blue light, a green light VGO, then it is 0.5 micron. That means it is 0.5 into 10 to the power minus 6. That means it is 0.5 into 10 to the power minus 4. That means it is 0.00005 in centimeter. You just see it. With respect to, suppose if the lens dimension it is 2.5 centimeter, whereas lambda it is 0.0005 centimeter. So with respect to the dimensions, you can consider lambda as 0. That is the case. That's why you are able to construct the rays here. So geometrical optics actually based on this concept that it is the path of propagation of energy in the limit lambda tends to 0. That means When the dimension of the optical system is large, then only you can use the ray. That's what is there. In case of multimode fiber, you see where the dimension is large. You see dimension is large. Here it is actually 50 microns. 50 microns, this diameter. Let us say this one, 50 micron. And lambda, it is lambda. It is generally point of infrared rate. If you just see 0.8 to 1 micron regions, 1.6 micron regions. So with respect to 50, you can consider this is negligible, right? 0.8 to 1 micron. That's why in multimode fiber, you can use the ray optics because dimension is large. But in case of SM fiber, where the dimension is say 2 micron, so with respect to 2 microns, you cannot consider 1 micron or 8 micron as zero, right? So for single mode fiber, you cannot use the ray optics. You have to consider the wave optics. This wave optics you have to consider. That means wave optics means you have to consider the light will be emitted. Whenever emission of light is here, it will be spherical wavefronts will be generated. And if it is light coming from sun, it will be the plane wavefront will be the parallel light, plane wavefront will be there, right? This kind of waves you have to consider, right? That is the wave optics. And later on, Maxwell's developed this one electromagnetic wave theory that is based on this Maxwell's equations, right? Electromagnetic field there, right? Electromagnetic wave theory. These things are there, but also you must be knowing other complicated nature of optics is also there. Quantum optics, where light has been considered the stream of photons, h nu, right? Where when you consider the interaction of light with matter, absorption, emission, that times you have to consider the quantum optics. So these things are there. But anyway, so in case of single mode fiber, we must consider the wave optics. And in case of multimode fibers, you can use the ray optics. If you can use wave optics in both SM fiber and MM fibers, but when you use wave optics, it will be much more complicated because many equations will be involved. I'll just discuss the mode theory in details. That time it will be more clear. Now, I think it is now clear when you consider the ray optics, or what is a ray and what is the criteria for wave optics, right? So in this context, I think you know these basic optical laws, that is Snell's laws or reflection, etc. Right. Little bit more about it. You see it here. Suppose a group velocity. What is this group velocity or the phase velocity? That is also required in optical fiber because we'll see the dispersion effect. That times this group velocity aspect would be there. To some extent, I've studied. Once again, you just see it. What is this group velocity? Quickly, I'm just showing it. Group velocity. Say group velocity. Group velocity and phase velocity. Phase velocity. Say, for example, if you consider adaptive mediums, when a wave is propagating along z directions, then you see any wave propagating along z directions, we can write it A cosine omega t minus kz, isn't it? Z direction, z the direction of propagation, k the propagation constant, 2 pi by lambda, omega the frequency of the waves. Now, this is actually say single frequency is here, right? Omega, right? And in this case, wave velocity, the phase velocity of this wave, you can determine by finding this this argument equal to constant. So omega t minus kz equal to constant, and finding dz upon dt, that is the velocity, dz upon dt, that is omega upon k. Quite clear? Omega upon k. That is actually, this is actually the phase velocity or the wave velocity. Phase velocity or the phase velocity or wave velocity. If you consider a single frequency wave, that is most important. You see, and that is called actually monochromatic waves, right? Monochromatic waves. Right? But in practice, generally, you are not getting the monochromatic. Any source emitting, it is not monochromatic. It's a even it's a red light. It is not a red light. It is not a delta function. Rather, it's a some spread is there, right? Some delta lambda is there. Delta lambda is there, right? Some spread is there. Monochromatic, so different lines, different wavelengths will be there. So all the times some spread will be there. That means some you'll get the light always non-monochromatic wave or quasi-monochromatic waves. So if you consider that once, suppose two waves, one is frequency of omega plus delta omega. Delta omega is very small. Another is of say omega minus delta omega. Two frequency you are considering. Right? The corresponding propagation wave, it is propagation constant is k plus delta k, and that is k minus delta k. Right. So we can write this EY1, that is a cosine, a cosine. In this context, you can see the coherence term also. It is the coherence means it will be highly monochromatic. It will be sinusoidal minus infinity plus infinity. That is true. It is you see, it is a coherent waves. The single frequency is here, and it is sinusoidal from minus infinity to plus infinity. Right. But that is not in practical case. In practice, you get truncated. So you consider these two waves, a cosine omega t, omega cosine omega plus delta omega uh, t minus k plus delta k into z. This one, and that one is y2. Just say amplitudes are equals. Say a cosine omega minus delta omega p minus k minus delta k into z. That we are considering two waves, slightly different frequencies. So adding these two waves, you'll get the resultant field. So the resultant field, it is UI1 plus UI2. So it will be of these things, and trigonometric relationship we just apply. Say x equal to suppose if you consider here after adding say EY1 plus EY2, and if you consider x equal to omega t minus kz, and y equal to delta omega t minus delta k z. If we just expand it in this cosine, right? Then what will get it? So you'll get it. Hello? हाँ बात बोल रहे हैं? So it's the resultant field will be just after this. Just simply if you just expand it, you'll get it twice twice a cosine omega t minus kz into cosine delta omega t minus delta kz. Means here x, if you consider x plus y, cosine x plus, you see cosine x plus y will be there. Cosine x plus y plus cosine x minus y will be there. X minus y. So actually that is this one will be there. Cosine 2 cosine x cosine y. That is actually cosine of x plus y plus cosine of x minus y. We just expand it. If after substitutions, you'll get this one. So what you're getting it actually, you'll see slowly varying. This delta omega is small, a slowly varying component with this the rapidly varying component. That's just like amplitude modulated waves. Right? You have seen this, the high frequency carrier is here, and another is a low frequency modulating signal is here. So that's this will be there. So in this case, so you are getting the modulated kind of wave. And in this case, the phase velocity will be just as you have seen it earlier. And if you consider the other terms, delta omega t minus delta kz, if you go to constant, and if you find the dz upon dt, that is actually called this Vg. That Vg group velocity, that is actually this delta omega upon delta k will be there. And in the if delta omega is very small, then this actually called the group velocity Vg. That is actually in the limit in the limit delta omega tends to 0, delta omega upon delta k upon delta k, that is d omega upon dk. This is called the group velocity actually. This is the group velocity. In fact, that is the velocity of the modulated waves. So if you consider in case of optical fiber, you see some, I'm talking the voice signals. If you want to transmit these signals to optical fiber, then this signal will be modulated with the optical signals, optical sources. Ultimately, in the source, ultimately in the fiber, modulated optical wave will be there, right? And velocity of that modulated wave is called the group velocity. Right, or group velocity, and it is the velocity with which information modulated wave will propagate at. So that is the group velocity. Anyway, today this much. If you have any questions, anybody you can ask. If you have any questions, Subodhan, if you have any questions, you can ask. Otherwise, I'm stopping it. Any questions?
No, sir.
Let me check. Now it is 37. 10 more students have joined. Those who have joined less, I mean, next time onwards, after just I'll see it, I'll make them absent. I mean, arbitrary times you cannot join. Please listen. And within 5 minutes, we have to join all of you. And if I check in betweens, then those will be absent. I'm just giving the warning. Yes, just wait. Today it is 21. 22. Okay. Okay, also, but then I'll upload, second half, I'll upload that copy, that book, right? Have you got it, that book, soft copy of the optical fiber, Kaiser? Have you got it?
Sir,
No.
I'm not getting the same edition. I'm getting the next edition. Actually.
Now black paper cover. Have you got it? I don't know. Anyway, I'll just upload it. You check it. There's only one copy available in the internet. And the recent one another is white paperback that is for useful for networking when you consider the maybe fifth module. That times that copy, that edition will be required. But most of the things will be from this edition, the black paper. I don't know whether it is third edition or second edition, and that will check it. But anyway, I'll upload it today. Right?
Yes, sir.
At this. Okay, then next time. Achha, one more thing is this Tuesday I'll be out of stations, so probably I'll not be able to take your class. Tuesday, some other times I'll see some extra class. Tuesday I'll be out. I'll not be here, so Tuesday class will not be there. Okay. You please inform. Right?
Yes, sir.
Tuesday there'll be no class.
Yes.
For 5 weeks. Okay.